Yeah, that happens. So,
It's sitting there reading code and making this like move and
it's being very demanding.
back. So you sort of know that fragment or no, I'm trying to yeah, I'm doing okay. Yeah, just running
Good to go? Okay. Okay, let's roll. Okay, so I'm not sure why you guys are here because you've already taken the class, but if you want to see another lecture on GPU, now's your chance. But, okay, so, all right. First, we'll start with any questions about last time's Gpgpu kind of thing. So what I tried to do last time was talk about okay, I don't have any pockets anymore, so I'm trying to figure out where to put this. To try to talk about big picture how we use the graphics pipeline to do this. A little bit high level about hardware, and we're going to talk more about NVIDIA specific hardware today. And we started to look at algorithms. So how do we map things into this parallel world? Anybody have any questions before we get started? Okay, so what we'll do today is finish our algorithms talk. So we had a little example last time. We'll go through that again and look at the parts we didn't look at. I'll talk very briefly about data structures, and that'll be pretty brief given the amount of time. This is sort of a whirlwind applications tour. So what sort of things have people done? And then probably I'll spend most of the time talking about NVIDIA's solution to the Gpgpu problem. So CUDA is the software layer that they have, and G80 is the first hardware instantiation of their GPUs that runs well using CUDA. And I got a couple things here. Don't know if we'll get to them, but I'll do the best I can in the hour and 20 minutes that I've got. Okay, so here's the application that we were looking at last time, this idea of bumpiness. So we got this grid of regular samples. And so what we're going to do is try to figure out if we treat those samples as a height map, where each value is a height above sea level or something, how bumpy is the terrain? Okay, and we're going to do that by comparing each element to its 4 neighbors and figuring out how different is it than the average of its neighbors. And we're going to take all those differences, square them all, add them all together. This is a standard error metric called sum of squared differences. But we're only going to add up the differences that are 0. So we're going to leave out the flat parts. Okay? Not necessarily the smartest way to compute this thing, because this would be a big waste of time, but it illustrates our stuff very nicely. So here's our code. Okay, what we'll be doing is first we're going to compute the average value of all of our neighbors. Then we're going to take the diff between our neighbors and our value, square that. Set a scalar value result equals 0, loop through all the samples where diff is not 0, and add that to the scalar result and return result. So what we did last time was we figured out how to do this, which was this map operation. Okay, very straightforward because we have a perfectly parallel application. And we can do the same thing at every pixel, okay, at every thread. And this, which was gather. And we talked about gather or scatter. So this is something where we actually have to talk to the neighbors there's some communication between threads to be able to make this work, but it does work. Okay, so what we're doing today is these two things. Okay, so we're going to start off looking at this problem, which is how do you take a bunch of numbers and add them all together? Okay, this is called a reduction. It's how do you take a bunch of stuff and use some sort of operation to combine all that stuff into one item when you're all done. Okay, so this is something in a scalar world, very simple. You have a million things to do. You loop I equals 1 to a million. Okay, and at every iteration, you do an add or a subtract or whatever you need to do at every step. Okay, so how many? If we have a million things, okay, how many operations are we going to do? Pardon?
A million.
A million. Okay, million minus 1. Million. How many steps is it going to take? Okay, also a million. Right? It'll take a million steps. Like if it takes 1 second per step, it'll take a million seconds to finish. Okay? So we talk about the work, when we talk about a work efficiency of something, we say, okay, how much work does it take? Okay? In this case, it takes order of n work. It also takes order of n steps. Okay? So that's the step efficiency of this. Okay, so usually in parallel computing, what we'd like to particularly do is reduce the step efficiency. We'd like to do things in parallel so that we have fewer steps. Often we are willing to have more work, to do more work in exchange for fewer steps. We have all this great parallel hardware. We're willing to make it a little bit wasteful if it means we can finish in a smaller amount of time. Okay? But fortunately, with this problem of doing a reduction, it turns out we can do something that has better step efficiency but has the same work efficiency, which is good. So here's what we're trying to do. We're going to say we're going to do a reduction with a particular operator. We're going to say that operator is binary. It operates on two things like plus. Okay? You add two things together. And it has an identity element I. So the identity element for plus is 0. The identity element for multiplication is 1, and so on. And then we're going to start with some sort of, and then the operator is associative. And by associative, I mean it is an operator such that A plus B plus C equals A plus B plus C. Okay? Is this true for integers? Okay? Is this true for floating point numbers? No, it's not true for floating point numbers. It's mostly true for floating point numbers, but you have a finite amount of precision, and I can pick floating point numbers such that this is not true. Okay? In general, it probably doesn't matter very much, but keep in mind that floating point number arithmetic, because it's finite precision, is not perfectly associative. Okay? For all intents and purposes in this class, it's associative, but just keep in mind it's not. Okay, so then we're going to have an ordered set of elements, okay? Some sort of set. And we're going to do this reduction on this set with this operator. All right, so we're going to use an operator in a set, and it's going to return this. Okay, so you can think of this as plus. You can think of it as multiply. You can think of it as max or min. Right? What's the biggest item out of a set of a million things? Okay, max is a perfectly legitimate operator. Okay, so we reduce this set with the operator plus. We just add them all up and we get 25. Okay, cool. So here's the smart thing we're going to do. Okay, this is a nice parallel algorithm here. So the problem is, we'll go back before you see that. You have this big set of things to reduce, and you think of the serial algorithm and you say, well, it's kind of serial. You have to go all the way through. You have to start at the top and go all the way through the whole thing. So of course it's going to take 1,000,000 steps. Okay, but the clever thing is, when we have parallel hardware, we're going to be able to do this with fewer steps. And here's the way we're going to do it. Okay, we're going to have this item. Okay, we're going to divide the whole set in half. We're going to take this half. We're going to plaster it on top of this half. And then we're going to do an addition, or whatever our operator is, for every element in that half. Okay, so we're going to take elements 0 to 500,000, take elements 500,000 to 1,000,000, slap them on top of each other, do 500,000 adds in parallel at the same time. Okay, that's going to give us something that's half the size of the original array. Then we're going to do the same thing. We cut it in half. We take this half, slap it on top of this half, do a pairwise add all the way through, bring it here. Okay, so every step, our problem is cut in half. Okay, and if you do the math there, what you'll find out is that this is log 2 number of n steps. Okay, you start off with 1,000,000 elements. It's going to take you 20 steps to get down to the bottom, because 1,000,000 is a 20-bit number. Okay, now the nice part is this is also work efficient. Okay, we're going to do the same number of arithmetic operations as we would if we did it in a serial manner. And so you look here and you say it's 1,000,000 elements. We're going to do 500,000 adds, 250,000 adds, 125,000 adds, and if you add up that whole series, you're going to get 1,000,000. Okay, it's cutting off. It's half as much at each step. Okay, so this is pretty cool, right? Now, one thing you should notice is this does it in a different order. Okay, usually if we do it in serial, we're going to say 1 plus 2 plus 3 plus 4, but here we're going to start with 1 plus 500,001. Okay, and that's why this operator needs to be associative. Okay, we're not going to get the same answer if it's not an associative operator. Okay, everybody clear with the picture I got here? Okay, we can do a lot of these operations in parallel if we want to. Okay, we can do this in a 2D grid and say, okay, we're going to do each stripe in parallel and do it over a 2D grid, which is good. Right, and that's often good for graphics hardware because GPUs are really good at dealing with 2D pieces of data, with textures. They're very much optimized to be able to do that.
It seems like in the beginning, let's say with your full, so with just the most end, maybe all of your units are being used, but every step down the line, you're only using half of your available hardware.
Okay.
So I don't know, just off the top of my head, would it be easier if you had like 100 numbers to add and 10 little units? Why not just divide it up and say you do 10, you do 10, you do 10? That way they're all working at the same time for as long as.
Okay, so this is a really good question. All right, we know we have parallel hardware now. Okay, and so we want to keep that hardware busy at all times. So we have a million things to add. So first we have 500,000 plus 500,000, and we've got 16 parallel units. No problem keeping them all busy. Okay, 250,000 adds to do 16 parallel units. Keep them all busy, no problem. The issue, if your problem size is much larger than your amount of available hardware, okay, then you're keeping it busy, busy, busy. Eventually you get down to the very end, and it's not busy anymore because you have 7 ads to do and 16 pieces of hardware. But that's this tiny fraction of the overall thing. So you're keeping it all busy here. You could say, well, we're going to take our thing and divide it into chunks, but you're still going to keep it busy either way. You could certainly organize your if we looked at this picture and we said, okay, each compute unit gets one of these, it's the same thing you just said, okay, that we've divided them up a priori at the beginning. So either one of those is going to work. The real key is making sure your hardware stays busy at all times. So, I mean, but you're exactly right. You do want to keep your hardware busy at all times. In general, we have a lot of parallel units, but we're also working with problems that have probably many more pieces of data than our parallel units. So at least you hope so. You hope you're doing big problems of that kind. Okay, but that's exactly right. You do want to keep these things busy at all times. So, and when you get down to the smallest amount and you're just doing 1 or 2 at the end, there's a bunch of guys sitting around. Fortunately, it doesn't really affect the overall runtime. Okay, this is kind of a one-dimensional reduction, right? We're sort of taking this and slapping it on top of this, and each one is one dimension. We can actually think of doing 2D reductions as well. Okay, so here we divide the whole thing into a big 2D grid. We take 4 elements, add them together to make 1, and that'll produce something that's half the size in each dimension. So instead of going 2 to 1 in each step, now we're going 4 to 1 in each step. Okay, so when I use the number 2 and 4, this is called a radix, and so we can have a different radix of reduction if we choose to. And so the answer here is really dependent on your hardware and your software system, that some hardware and software might be better for a bigger radix and some might be better for a smaller radix. Okay.
Does that have anything to do with radix sort?
No, totally different thing. It's just the name of the number. Okay, so everybody cool with reductions? All right, pretty straightforward thing to be able to do. GPUs turn out to be really fast at this because they're able to keep all their hardware busy. Okay, so the last algorithm I'm going to show is a really tricky thing to be able to get right. And so that's this issue of, well, what we essentially want to do here is filter. Okay, we want to take in a bunch of elements, and for each element we're going to say whether that element is true or false. And we're going to want, that's our input. Our output is only the elements that are true. Okay, so let me sort of draw that up here. Okay, so we have A, B, C, D, E, F, G. And we want to say, I would like an output with only consonants. Okay, no vowels. Hate vowels. Vowels suck. So then we put out B, C, D, F, G. Right? This is our goal. It's a filtering operation. Okay, so why is this hard? Okay, this is hard because, well, what we need to know here is we'd like to be able to take B here and write it to here. So B wants to know that it wants the number 0. Okay, this is element 0, this is element 1, and so on. C wants the element 1. D wants the element 2. Okay, and then we're going to scatter these items into their destination. Okay, so this problem is equivalent to the problem of figuring out these numbers here. Right? Okay, if we know these numbers, and we know whether they're true or false, we know where to write these numbers into the output array. Okay, so this problem comes down to this problem of how do we calculate these numbers? I'm going to say to you that this is hard to do in parallel. And I say that it's hard to do in parallel because any of these elements can affect any of these other elements. If I change this to Q, okay, then every one of these change. right? So that's what makes this thing really tricky. So we'd like to be able to do this in parallel. Okay, so let's say we want to do this compaction here, right? So we put in an input of all the letters here, and we put in a set of trues and falses. Okay, so the red ones up there are trues. They correspond to these red items here. Okay, and what we want to do is we want to keep all the trues. Okay, so the output is the scatter addresses. Okay, where do we want to write A? A goes to 0, C goes to 1, D goes to 2, and G goes to 3. That's our goal, to be able to do that. It's hard because it's this all-to-all communication to be able to make this work. Okay, everybody clear in the picture that I'm putting up here? Okay, so this operation is called scan. Okay, it's also called prefix sum. And so it turns out we can get these numbers in an interesting way. Okay, basically, we're going to go back to A here. Okay, the number that we put here is the number of consonants that came before B. In this case, it's 0. Right? The number we put here is the number of consonants that come before C, which is 1. Okay, D gets a 2. Okay, E gets a 3. F gets a 3. Okay, because there's 3 consonants that came before F. Okay, so this is called prefix sum because these numbers are the sum of all the elements to the left. So it's a sum up to there. So and prefix because it's everything that came before you. Right? So this problem comes down to the fact of, can I add up everybody that came before me? Okay, so scan is usually what people are calling it these days. And here's the way that we're going to compute it. The prefix sum of the first element is the identity, okay, in this case 0. The prefix element of the second one is just the one before that. This is the sum of these two. This is the sum of these 3, and so on. Okay? So the example of scanning this particular array is at any element, it's the sum of everything that came before it. Okay. So in a serial world, this is going to be order of n work. Okay? Because you just compute sum, and you keep all your intermediate results around. And in a scalar world, this is going to be order of n time. Okay? Order of n steps. You're going to do 1 step per. Okay? So we'd like to be able to reduce the number of steps, but still keep the work the same. Right? So let me tell you a stupid way to do that. Okay, the stupid way to calculate this in parallel is to say, okay, everybody calculates its own prefix sum. Okay? Every element calculates its own prefix sum. The problem is that's going to take order of n steps and order of n steps and order of n squared work. Okay? Because this guy is going to have to sum everybody before him. So it's order of n squared work. That's not so good. But it turns out there's a very nice parallel formulation to this that shows how you can do this in order of n work and order of n steps. So I'll tell you just a little bit about it. First, I'm going to show you what we actually use scan for. And it turns out this is a useful operation in many, many different application domains. So this is really key to doing good parallel computation on a data parallel machine. In our group, we've done it on radix sort and quicksort before. We've certainly done some stream compaction things. We did the original sparse matrix work on GPUs using scan. Turns out it's useful for lots of things. We're very happy with it. So here's one way we can do this. You end up doing sort of this tree kind of computation. So you have these original elements here, and you do a tree structure coming down, and then you use the partial results you have there to sort of propagate everything out. Okay? So it ends up being 2 log number of steps, but it ends up being n amount of work. Actually, it ends up being 2n amount of work. So it has the same work efficiency, but much better step efficiency than what you get on a serial machine. So it turns out we can run this roughly an order of magnitude faster on a GPU than a CPU, and it's really key to being able to do a lot of algorithms. So I'm not going to talk about specific the way this works, but I can certainly point you to a paper that has this in lots of detail. So this is a really good thing to be able to have scatter for. Scatter makes it absolutely key to be able to do scan. Okay, let me just quickly mention a couple of other things. One is how to do parallel sorting. Okay, so sorting is a really hard problem to do in parallel. I have some things that you know how to do well in terms of sorting are things that just don't work out very well on GPUs. So a lot of the stuff we do is very straightforward, easy sorts. Some of them are sorting networks that are oblivious to your inputs. Some of them are merge sorts, where you take two sorted elements and you do a merge between them. And so there's still a lot of active research in being able to make this run well. One of the cool things is that there's a group at North Carolina and Microsoft that won the penny sort benchmark. So it's you have a giant sort. How cheap can you do it? How cheap a machine can you do this sort? So how much sorting can you do for a penny is the question. So a GPU CPU system was the penny sort winner a few years ago, which was really exciting. Okay, that's kind of all I got for algorithms. Anybody have any questions on this? Okay, I'm going to talk just very briefly about data structures. So when you're doing a GPU computing kind of application, you have this big wad of data out there, and you usually run some kernels over that data. And the question is, what is that big wad of data? And most of the stuff that we've talked about has been data that's basically an array. You operate over a big array. And so people have done dense arrays, which we're very good at. GPUs are great at dense arrays. We've also done some stuff with sparse arrays, and that's a little bit more complicated because it's less regular computation. We'd like to be able to do more adaptive data structures that change, okay, building up trees and graphs and things like that. So that's a tricky thing to be able to do, and that's, again, an active research kind of challenge. Okay. So now I want to talk about just a few areas where people have done GPU kind of work. So some of this is things that's pretty well understood. Some of it's more speculative. One of the earliest things people used GPUs for was solving differential equations, doing fluid flow kinds of problems and so on. And so solve both ordinary differential equations, and that's used to do particle system kind of simulation, and partial differential equations, which are really nice for like fluid kind of simulation. So Everett's done a lot of work in this area, which is pretty cool. And it turns out both of these lend themselves very nicely to parallel approaches, and so you can get some really good speed-ups on GPUs. Linear algebra turns out to be something that's very interesting on GPUs. So people want to solve very large arithmetic kind of problems. And so things where GPUs have dense matrices usually look very good. Sparse matrices are a little bit harder to get to work well. And people have looked at different kind of matrices as well. So these are some slides from Jens Kruger, who was at Technical University in Munich, and now he's doing a postdoc at Utah. Sort of showing how you take one-dimensional arrays and pack them into two-dimensional texture maps, and then how you use this sort of representation, if this would ever move forward. There we go. How he actually ended up representing matrices in terms of GPUs. So he represented matrices as vectors and then put each vector in a 2D format, if this would ever advance my slides. But they got cool animations, which is good. He would take banded matrices and, if it would ever advance that, okay, banded matrices, and he would represent those as vectors, which he would then pack. And he would do that by taking the banded matrix, like the diagonals, and represent this whole thing as a vector. And so when you do banded matrices that only have non-zero items in a diagonal, this is a much more efficient way to be able to do it, which is kind of cool. Okay. So this is early GPU work, so it was very difficult to do this because it's all done with the graphics interface. So doing things like, so just to show how he did vector addition, for instance, this uses sort of this classic GPU technique of let's take two vectors and sort of put them on top of each other. The way we do that is we draw a big quad. The vertex shader does nothing. And then the pixel shader, what we do is we fetch one value from each of these and add. And so we're able to do many, many in parallel that way, which is cool. Reduction kinds of things uses the same sort of reduction operation that we talked about. So when you, oops, come on back. There, and then there. Okay, uses the same sort of reduction algorithms that we talked about, that he would take 4 items, radix 4, add them all together to make one item, and then do log base 4n of the number of passes and be able to add everything all the way up. So, okay, so this is a very exciting area of research, too, because it's now that people are starting to do more interesting and complicated GPU kind of computing techniques, like harder matrix kind of things that are more difficult to do. There's been some really cool work on doing data query kinds of stuff. So can we put a database on a GPU, right? So Some people feel that in the long run, all problems will be database kind of problems, that the whole problem is you've got this enormous amount of data. How do I find what I want out of that? So not all database queries go nicely to the GPU, but there's several that do. And so particularly when we do predicates, so filtering kinds of things, combinations of many predicates, it turns out to be pretty good. In terms of application kinds of stuff, there's a lot of Gpgpu application areas that people are interested in. So physically based simulation, this is really nice for visual kind of effects. If you're running games and you wanted to have cool like smoke effects or boiling water or turbulence kinds of things, you often do that sort of modeling with a GPU. So if you're seeing that in modern games, it's entirely possible this is done with Gpgpu kinds of things. Signal and image processing. So people are interested in identifying features. So a lot of stuff in medical image processing. So you feed in an X-ray photo and you say, where's the tumor? Right? Can you recognize that sort of thing? Can you segment out the tumor? Can you look for can we look for a speed limit sign in a big picture? That's something our group is doing. So how do you figure out where the speed limit sign is? How can we use a GPU to be able to do that? So these are vision kind of techniques that are interesting because you can get good parallelism out of there. If you're looking for a speed limit sign in a picture, you'd look everywhere on the picture. You can do all that at the same time because you do it all in parallel. Image processing kinds of stuff. So plus signal processing. So people are doing FFT kinds of things. There's a lot of interest in being able to do that well. NVIDIA has a FFT library that's part of their software their software libraries that they give out. People have done some really cool graphics stuff that isn't very well suited for the traditional Polygon pipeline. So some of the earliest Gpgpu work was doing ray tracing on graphics hardware. Okay, so these are some really good papers, some of my favorite papers in computer graphics. So the goal here is that there's, if you're Intel and you're making, so Intel has this enormous experience in ray tracing. They're really good at ray tracing. And they're building this new processor called Larrabee that's probably going to be really good at ray tracing because they're so good at ray tracing as a company. And so Intel's sort of saying, oh, ray tracing is the next big thing. So the companies that build traditional GPUs are really interested in making their GPUs run very nicely on ray tracing and using techniques like CUDA and other GPU techniques to be able to do ray tracing. And ray tracing is a very parallel problem, but there's a lot of very interesting data structures and hard control kind of constructs that you do in ray tracing. So, but absolutely this is informing future hardware design. Because we talk about doing GPU computing and it does things that aren't graphics, and all the graphics companies care about is graphics. Well, ray tracing is graphics, and so it's potentially part of lots of future pipelines. People have done some other kind of things like photon mapping, radiosity, subsurface scattering. These are all things that are graphics algorithms that are not accelerated by the traditional graphics pipeline. But can we put them in a graphics pipeline of some kind, and use them? Okay, so photon mapping is a global illumination technique. You end up scattering light all around the room, and wherever it hits, you sort of leave a bunch of photons, and then other places might hit those photons. And so a lot of very high-end rendering techniques use that. Radiosity is sort of calculating the solution space of how light is transformed around the room. The picture that I showed really early in this class where it was the first floor of a building and we didn't see the second floor and it looked like this very nicely lit bottom floor with a big staircase up the middle, that was a radiosity picture. Subsurface scattering, very important when you do things like skin. So people look really bad in computer graphics, right? So Pixar doesn't really draw people. Pixar draws cartoon characters and fish and mice and things like that. But Pixar really doesn't really draw a lot of skin because skin is hard. And we as people know we can look at a computer-generated picture and say that's not really a real person because we're very good at detecting skin. The problem with skin is that skin itself has no color. And the color is given by, melanin for one thing, but mostly blood vessels that are underneath the skin. So you've got this sort of clear layer that's skin, and then color underneath here. So what really happens is light comes into the skin and it bounces around for a while and it leaves. And you need that subsurface scattering, the scattering underneath the surface, to be able to make it look right. You actually have to calculate how things scatter inside the skin. So if you want skin to look good, you need to do this sort of thing. So there's some very cool work that's been done along those lines. Okay. Geometric kind of computing. So one of the big ones here is collision detection. So what you want is you've got 1,000 boulders that are rolling down the hill, and if you're actually computing how those boulders work and you're trying to do the physics, you need to figure out which boulders run into which other boulders. So there's obviously the brute force solution of 1,000 boulders intersected with 1,000 boulders means I need to do 1,000,000 intersections every frame to figure out which boulders hit which other boulders. Well, you can make that faster with some other techniques, but it's a very computationally intense kind of thing. And you're very interested in graphics about which things hit which other things, and how can you detect that? So it's a big geometric kind of problem that people are very interested in. So using some of the data query kind of stuff, there's some really cool database applications out there. So that's ongoing work. But, there are database conferences that have GPU sessions every time, and so this is something we're also pretty excited about. So that's sort of a whirlwind tour of some of the cool things people are doing with GPUs. Does anybody have any questions about applications? Okay, a lot of you will end up picking a project that's sort of along these lines, right? Some application, you'll look at how does this work on the GPU? How does this work with GPU computing? And so if you're thinking of things, please let me know, and I'll try to point you to the resources that people have done before and help you identify what seems like an interesting problem to work on. But obviously, there's a real breadth of applications that people have looked at.
Has anyone ever tried to do recursion with GPUs?
So, I mean, recursion is a technique. What do you want to do with recursion?
I mean, just because GPUs themselves don't have like this recursion feature. So has anyone ever tried to emulate or that feature on GPUs?
Well, again, what for? When people try to solve problems with GPUs, it doesn't really matter how you solve the problem as long as you get the problem solved. So what sort of problems are well suited for recursion that aren't well suited for other things?
Well, say like dynamic programming.
Okay, so that's something I don't know anything about at all. I always get it confused with linear programming, so tell me which one's which.
Dynamic programming is the one where you, like the current value depends on the values of the previous one.
Ah, okay. So, cool. Now this giant me up on the screen there. Cool. Nice work, camera guy. Let's see. So, yes. So let me draw a picture. So I believe this problem ends up being you have this big thing here, and you can compute these guys here. And it turns out this guy depends on this guy, and this guy, right?
Yes.
Okay, so, and you sort of walk all the way down.
So it's like marching cubes.
Yes. Okay, so the question is, how do you parallelize this? Right? So I don't know if I'd call this recursive, but it has an interesting dependency structure. So this is characteristic of a string matching algorithm that's been done in genetics, and it's called Smith-Waterman. And so the goal here is you have a string of DNA nucleotides, A, C, T, G, A, G, C, T, A, so on. You have two strings. And you want to find out sort of if they match and how well they match. Okay? So there's a dynamic programming algorithm that works on these, and it uses this sort of formulation. And so what you end up doing is you compute the entire grid, and then you walk down and you pick all the minima. So people have implemented this in a couple ways. Okay? So the problem is that this guy here is dependent on all these guys. So you can't parallelize very nicely across this. So here's how we look at this in a GPU world. Right? Everybody's dependent on its left neighbor, on its left up neighbor, and on its up neighbor. And then you make this giant grid that's like 1,000,000 by 1,000,000. So one way people have done it is they do diagonals. Okay? Because everything in a diagonal is independent. Make sense? Okay. So you're not very efficient here because you only have one item and then 3 items and then 5 items and so on. Not efficient. But once you get down to the meat of the matrix, you have lots of things to be efficient at. Okay, so that was something done by Yang Wu, a Davis graduate at Lawrence Livermore a few years ago. The other cool thing that you can do, though, Andrew knows this, is that you can take this and you can recast it so that you do an entire stripe at a time, because if you walk across here, it turns out the operation you need to do is scan. And if you do a scan all the way across here, then you can do another scan here and another scan here, and then you've regularized the computation much, much more. So this is a nice example of how to take something that looks hard to parallelize and turn it into something that we know how to do pretty well. So this is, at this point, considered to be a really simple algorithm. Like, when people talk about doing molecular biology on GPUs today, they're usually, this is about the simplest thing you can do on GPUs. And so people kind of laugh at Smith Waterman now. They didn't like a year ago, but they are now. And they're saying, well, we want to do something more complicated now. So one of the big problems is doing, you have a protein, and how does that thing fold? And so that ends up being like a big collision detection kind of problem, and you do some energy minimization, and that is like an enormous computational problem. So if any of you have done folding at home, that does protein misfolding kinds of things. And that's something that actually parallelizes fairly well too. Although there's like all these kernels in folding at home, and the GPU people pick sort of the easiest ones. And those look really good when you speed them up, but still have yet to do the entire pipeline. There's a question back there.
Yeah. All the examples you showed are different algorithms, right? I'm just wondering if the hardware is kind of optimized for that application. I mean, we find a lot of GPUs that are specific to a particular application.
Yeah, so that's a...
GPU, it's like very generic, right? Does a lot of things.
Yeah, so I would say it's fair to say that they're not particularly optimized for any special application. They're specialized for graphics. And so they provide sort of this general parallel substrate, and we'll see that in the next few slides. What are the ones GPU people are really interested in? So traditionally, there's two groups of people that are perceived of having a lot of money. And one is energy companies, and that's for like oil and gas exploration. So you end up doing a lot of geophysics kind of simulations. There's a lot of signal processing in there because when you take a boat out into the Gulf of Mexico and you're looking for oil, the boat costs you $1 million a day. And every time you punch a hole in the ground, it costs you another $1 million. So it's worth it to you to spend a lot of compute to make that good. So for those sort of signal processing and a lot of simulation kinds of things, I would say that is a focus of GPU people. The other group of people that have historically had a lot of money that you'd like to sell to are the finance people. And that's maybe not true today because they're all bankrupt. But basically, you want to be able to compute options. And so there's been some work, and I actually don't know this work at all, about stock option derivatives and being able to calculate what they're worth. And there's a model called Black-Scholes that, again, I don't know at all. But that is something else where they feel like, okay, if I can sell you a GPU and you can finish 15 seconds ahead of your competitors, that's potentially a lot of money for you. So those are goals. I think it's fair to say like you could also pick some things they want to be good at. They want to be good at linear algebra in general. They want to be good at FFTs and other signal processing. And those are sort of the categories that I showed you, or just where I know there's been some commercial interest.
Like if you look at the hardware, like for a scan or something, right? You can optimize your hardware just having certain arithmetic elements only, right?
Okay, so as someone that helped develop all that work, I would be thrilled to see that happen. That's a good candidate, right? So, I think it's an enormous research question. What I usually like to describe I do in terms of research is to try to look at the building blocks of parallel computation. And the question for me is, what are those building blocks? And so is scan a building block? What sort of communication patterns should we really have within the thread blocks in the processor so that we can support more flexible sorts of things? So, that's what we try to figure out. But I think it's a very young field and has a lot of opportunity. It's a great question. Okay. So, what we'll be talking about pretty much for at least the next half hour is how NVIDIA has developed a GPU that's well suited for GPU computing. So what we've seen is some of the things we want to do, some of the algorithmic techniques that we want to do to make that work. We know how the graphics pipeline works, and what we're specifically going to look at is the compute units. Okay? So you can think, well, we want to build compute units that are really good at vertex processing and fragment processing, and that's true. But how do we start putting things in that are going to be well suited for more general purpose use? Okay? And then, what does the programming model look like? What's on the software side? Okay? How do we address this sort of thing? How do we structure programs? What does it look like when we program them? And so these two things are very tightly coupled, the hardware and the software. And I'm going to be talking about them both like this. It's not like hardware and then software. We're going to be talking about both of them. So NVIDIA has this nice picture of weaving. They have a lot of weaving techniques in their hardware. You say, well, this is a massively parallel thing to do because we've got lots of strings. And then these are threads. So first is something that we've talked about before. GPU and CPU threads are different. GPU threads are very lightweight. Okay? It's very simple to create and destroy a thread. And it is likely you're going to have thousands, hundreds of thousands of threads all at the same time. And even running simultaneously, you have thousands of threads that are live at the same time. It's very different than a CPU. Okay, CPU, maybe each core's got a dozen threads or something, but we're not talking about hundreds or thousands of threads.
John?
Yes?
When you say, I hear the terms like lightweight or heavyweight creation of a thread.
Okay.
What does that really mean?
Great question. Okay, so when you create a thread on a CPU, that's generally perceived as something that is heavyweight. And by that I mean sort of the amount of work it takes to make a thread is large. Okay? You have to go in and change these operating system tables, and it's got to generate its own thread ID, and got to register itself with this guy, and got to save away all this state, and so on. So you can say, okay, well, if I launch a thread, it's going to take me 10,000 cycles and 3 interrupts, and it's going to take me, a few microseconds to be able to do it. So that's what I mean when I say heavyweight. The goal here is to make them lightweight threads, where it is almost free to be able to create or destroy a thread, where it doesn't have to go talk to the operating system. It's very easy to create lots of threads at the same time. That's something CPUs don't do, right? You do fork and fork with a CPU, like that forks one thread. Okay, GPUs want to create 10,000 threads at a time. Okay, can we do those all in a big block? So it's sort of how much effort does it take to make or destroy a thread? Okay, NVIDIA's goal is to make that cost absolutely as cheap as possible. Okay, and also to make sure that if you have 100,000 threads active, that isn't going to penalize you. Okay, they're not taking up space or anything. It's that you want that cost to be minimal. Okay, so here's the picture we knew from our programmability lecture. Right, so this is a pixel processor in the pre-G80 version here. Okay, we've seen this picture before. We have a fragment program. We have a bunch of inputs that come in, a bunch of outputs that go out. We put out some sort of color. That's the output. We can talk to global texture. We can have some constant registers that we can't change and registers that we can. Okay, seen this picture before. Super. Okay, so what's the drawbacks of this? All right, so one of the issues here is that when we talk to texture over on the right here, okay, we can only gather. Texture is read-only. You don't get to write back the texture, at least not within a fragment program. So you're able to have your ALUs say, oh, I'm going to go out to DRAM, I'm going to grab all this stuff, but what we can't do is scatter. We can't take a value from our ALU and write it to a different bank of DRAM. Okay? In fact, the only way we get to write back to DRAM at all is that we write back a color and a depth at the end, but then we're only writing back to our own color slot, our own pixel. Okay? We can't write a fragment program that's going to let me write back to somebody else's pixel. Okay? So we have gather, not scatter, in a traditional GPU. So that's sort of a drawback. Okay. Another thing is, what happens when you have all these different ALUs there and you want them to communicate? Okay? You compute something here, you compute something here, and you want to switch. You want those two guys to talk to each other. Okay? You want him to have his value and him to have his value. Okay? What you have to do in traditional Gpgpu is finish an entire pass, write everything out to DRAM, start another pass of the graphics pipeline, okay? And then when you go through that pass, you can go read what the guy wrote on the previous pass. Okay? So if you're doing a sort, for instance, okay, and he has the number 4 and he has the number 3, and you need to swap those two, it's going to take you an entire pass to be able to do that. But that's how people did sorts before, okay, to swap two numbers in two adjacent compute processors. So there's no real way for processors in traditional Gpgpu to talk to each other, except through DRAM at the end of a compute pass. Okay? Second big disadvantage. Okay, so what they talk about now is we're going to take this model and we're going to try to generalize it a little bit. All right? And instead of having a fragment program, we're going to have a thread program. And every thread is going to know its own ID. So if we launch 1,000,000 threads, I'm going to know I'm thread 396. Okay, so every thread knows where he is. Okay? We want to be able to support lots of instructions, the whole instruction set. We can branch and loop and so on. We can have thread numbers that are 1D, 2D, or 3D. Okay? So that's a useful thing to be able to do. Okay? A little bit more general. Okay? We're going to be able to talk to global memory. Okay? Not only to read from anywhere in global memory, but to be able to write to global memory. We're going to be able to scatter. Okay? That's important to us. Not so important in the graphics pipeline, but important to us for doing general purpose sort of thing. Okay? So we want any thread to be able to access any piece of memory, read or write. Okay? The next thing we're going to add is what we call this parallel data cache. We're going to say, well, it's a real disadvantage that two ALUs right next to each other that are running two neighboring threads can't communicate. So what we're going to do is, in a thread program, we're going to have several threads running in parallel, and we allow those threads to talk to each other and not have to go all the way out to DRAM. Okay? Can we basically have a little tiny cache, little piece of memory that adjacent threads can both read from and write into? Okay? So we're going to go to have one of those too, and we're going to try to make that really fast. So the picture they sort of have here, these are all NVIDIA slides, by the way. I totally stole them all. So we're going to have ALU, ALU, ALU. They can still go out and talk all the way to DRAM, but we're going to have a little shared data cache so that if he wants to share data with him, then he can write it into the cache, and this guy can read it from the cache. Okay? And that's huge, because it was very inconvenient to always have to go to DRAM to do communication. We can do much more interesting algorithms if we're able to have this parallel data cache.
But doesn't this give you hazards?
So it depends on how you structure your program, right? So let's say, for instance, okay, I'm thread A and I'm thread B. Okay, and I'll say I'm thread 0 and I'm thread 1. That's probably better, all right? And I say I would like to write my value into address 1, and I would like to write my value into address 0, and then I would like to read address 0, and I would like to read address 1.
But I'm sorry, but how do you guarantee that that's going to happen in the right order?
Okay, so what could go wrong here? That's the question. Okay, we have two parallel threads. Okay, if we do this in parallel, and then we do this in parallel, are we going to do the right thing? Okay, what can go wrong? Okay, what happens if we run all of this before this guy starts? Okay, what happens if we run all of this before this guy starts? Okay, because one of the cool things about the GPU is you're going to kick off a million threads. You don't know what order those threads are going to run in. Okay? So you have to structure programs in such a way that this is going to work, and that's a problem. And so what you need is some sort of hardware structure to say, hey, stop here, wait here until everybody gets here. And we do that with a structure we call the barrier. Okay, so what we do is we're going to put a barrier right here. Barrier. Okay? And what that means is all the threads need to reach here before any threads progress. Does the barrier solve the problem? Okay, in this particular case, the barrier does solve the problem.
Is there kind of synchronization thing in CPU, like a signal, sending a signal or mutex, critical section, something like that?
Right. So in a CPU, there's a number of synchronization mechanisms in parallel computing, like you say, mutex. What do we have? Mutex, semaphore. Okay. So at least in CUDA, you have a barrier. That's all you get. I believe there's people in OS theory that can show that the barrier is equivalent. You can treat, you can build other things out of barriers and so on. Like you could build a mutex out of a barrier if you chose to. I'm not sure if that's the case. I will say that this is a very useful communication primitive, and there are other atomic kind of primitives that cover a lot of the space of the synchronizations that you'd really like to do. This is the only one that CUDA gives you, though. CUDA will give you a barrier. Good question.
Does the barrier apply to all threads executing that code, or just...
So that's a great question. Let me defer that for a minute until we talk about blocks. Okay? Great question. We make sure that when I talk about blocks, we'll be able to talk about this. Okay. So parallel data cache, good. One thing you can envision, though, is that, why would it be good to have lots of threads be able to share data through a data cache? Easy question. Why is that good? The more, the better. Why is that good? Okay, well, go.
I mean, the more communication, I mean, you can take it at the lowest case. If you just have two, then all they can do is swap data, and that's it. But, the more complex the algorithms you could do with that.
So we got lots of things that can share through this data cache that don't have to go out to DRAM, right? The more things that can share through the same data cache, the less we have to go out to DRAM, and that's good. Okay, What's the bad thing as that gets bigger?
It's probably going to be slower, higher latency,
Okay.
and for manufacturing, if there's a defect somewhere.
So there comes a point where there's just too many people to share, right? I can teach to 16 of you guys, but I don't share very well if I'm teaching to 16,000 of you guys at once, right? There's limitations of scale. So there's sort of a sweet spot in there. You'd like enough to share to be able to make it useful where there's actually useful sharing, but if you make it too big, there's hardware implications because you can't continue to scale that very well. And so keep that in mind as we continue to talk. Okay, so this is sort of a picture there, Chip. It's you've seen this picture before. What this shows is units in the GPU computing picture of the NVIDIA pipeline, right? So this thread execution manager, okay? Well, that's in hardware. There's a lot of stuff between that and the rasterizer. The rasterizer is what creates and launches threads and so on. But here it's sort of the thread execution manager. Okay. So the big picture that we're doing with NVIDIA here is that they will launch lots of threads at the same time, and they will organize these threads into blocks. Okay? I'll tell you what a block is in a minute. But what the thread execution manager is responsible for doing is taking blocks and assigning them to multiprocessors. So here we have a picture of 1, 2, 3, 4. I think there's 16 multiprocessors here. Okay? So you got this enormous amount of computation out there. Okay? It's divided into blocks of threads. Say we got 100 threads per block. And then this guy decides which blocks go to which multiprocessors. Okay? Now, within each multiprocessor, there's parallelism. There's a number of ALUs. And then in big GPUs, there's lots of multiprocessors also. Okay? I want to make sure everybody's totally clear on this. Okay? Any questions about the way this is structured at all? Okay, so the promise CUDA makes you is your block will get assigned to some multiprocessor, but it doesn't tell you which multiprocessor, and it doesn't tell you which order it's going to go in. Okay? All right, so what is in, so if we look here, there's this, what's called a thread processor group here, and it has 2 multiprocessors in it. So here's what those look like. This is a multiprocessor, this is a multiprocessor. All right? What we see here is one multiprocessor, a second multiprocessor. So we have one parallel data cache per multiprocessor. Okay? All threads in a block can share a parallel data cache. How big is a block? It's up to 512 threads. Okay? So up to 512 threads can all share in this data cache. Otherwise, they have to go out to memory. Okay. So what's actually in here? So in G80, which is the first flagship NVIDIA CUDA-capable GPU, there are 128 thread processors. Okay? They're divided into 16 multiprocessors. So we have 16 multiprocessors of 8 thread processors each. Okay? Each thread block, each multiprocessor, has one 16 kilobyte parallel data cache. Okay. So remember I told you, just one slide ago, that they promise that your blocks, you're going to have 1,000 blocks in your program. Okay? It's responsible for dealing out blocks, but it doesn't tell you what order they're going to run in, and it doesn't tell you which blocks are going to run on which multiprocessors. And they made this decision for a very important reason, because they can scale the architecture with this decision. Right? You can take a cheap GPU, like in my laptop, that maybe has 4 multiprocessors on it. Okay? And the thread execution monitor will deal things out to those in any order. Doesn't tell you what order, doesn't tell you where they're going to go. And it will run the exact same way as if you have a big GPU with lots of multiprocessors on it. Okay? What it means is you as the programmer have no idea how many multiprocessors you have. Okay? So your program is going to run correctly no matter how many multiprocessors there are. Okay? This is a really smart thing for them to be able to do. Because it means that as they build newer and newer GPUs, they can keep throwing transistors at having more multiprocessors. And programs will continue to scale. As long as you write programs that have many more blocks than multiprocessors, you're in fine shape. Because this guy is going to figure out how to deal those out efficiently. Okay? So that's a really big idea they had there. Okay. Okay. The other cool thing is what's actually in this. Okay, so we'll go back one. There are 8 thread processors per block. sorry, per multiprocessor. And we throw a block of 512 threads at a multiprocessor. Okay, so we've got 8 thread processors to run 512 threads. Okay, so that means that we can have more than one thread per multiprocessor, or per thread processor. Okay, now our goal is to have this issue of latency hiding. What we want is to run a thread for a little while until it stalls. Then we're going to switch over to another thread. And then we run that one for a little while until it stalls. And then we switch over to another thread. And we keep doing that. And if we throw a block of 512 threads at 8 thread processors, okay, that's a lot of threads per thread processor. And what the hardware is really good at doing is to be able to say, okay, that's 64 threads per thread processor. It's really good at switching between threads whenever one stalls. Okay? So it's very slow at running one individual thread, but it tries to make sure it's busy all the time. All the time. So if it runs into anything that's going to stop it from making progress, it'll switch to another thread. Okay, then it'll run that as long as it can, switch to another thread, and so on. Okay? And that's the way it tolerates latency. It tolerates latency by having lots of threads so that it can always switch to a new one. In fact, if you have enough resources in your multiprocessor, you can have 2 blocks in your multiprocessor at a time, or 4 blocks, or 8 blocks, or however many it can fit. It depends on how many resources you take up. Okay? So if one thread block takes up all 16 kilobytes of the shared data cache, you can only have one thread in there, or one block in there. But if you only take up 8 kilobytes, then you can have 2 blocks resident at once, which means you have even more threads resident at once, which means you're even better at hiding latency. So it's in your best interest to try to minimize your resource usage so you can have as many threads resident at a time, and that's going to do a better job of keeping your hardware busy at all times.
I'm really lost with the hierarchy of blocks and threads and all that stuff.
Good question. I'll actually show. I'm sure that's going to come up in a second. So, great. Here's our picture. I'll just point to that. Okay, we run a kernel. The kernel will run over a grid. Okay, so one grid per kernel. The grid is a grid of blocks. A block is a block of threads. Okay, so every block, all the blocks are dealt out among multiprocessors. Okay, within a multiprocessor, there are 8 thread processors, and this whole block runs on the same multiprocessor, and these threads are dealt out to thread processors. These are done in a very regular way.
Is a multiprocessor a single pixel? Like, which is the pixel level?
Good question. So a thread processor is equivalent to a fragment processor. Okay? So if I'm doing graphics here, that's a pixel, that's a pixel, that's a pixel. So at any given time in the picture that I showed, there's 128 thread processors, so 128 fragments would be being processed at the same time, and it's likely you would have thousands of fragments in flight at the same time that are sort of waiting their turn. They're resident in the thread processors, but not actually active because somebody else is being run.
Or vertices.
Or vertices. Or vertices.
Does it have to be 2D, the grid? I mean, could you...
I think the blocks can be 1D, 2D, or 3D, and the grids can be 1D or 2D. Okay. Does that picture help? Okay.
One question. What's the kernel?
Okay, so the kernel is the program that runs over all the threads in a grid. So you write one program, it runs over everything that it runs over the entire computation domain.
Okay.
Okay. So maybe your kernel does the averaging operation that we showed. It goes out and grabs its neighbors and does the average, and then does the sum of squared difference.
Since the GPU handles what block gets what block you specify, why does it matter if you put it in the grid or not?
Ask the question again.
So you specify whether it's a 1D or 2D grid.
Yes.
But you don't have any control of what order they're operating in.
Right. Strictly for programmer convenience.
Okay.
It might be convenient for you to have a 2D grid for whatever reason, because remember, every thread knows where it lives. Every thread knows which thread it is within a block, and it knows which block it is within the grid. So if you're doing 2D computation, it probably makes sense for you to have a 2D grid.
It's just for like mapping into the array or whatever your data structure is?
Sure. So it's very data structure dependent there. Okay. If it doesn't matter to you, then do everything as 1D, and it's probably easier. But if you're dealing with 2D structures, then it makes sense to have 2D grids and 2D blocks. Okay. So, good. We saw that stuff. Okay. All right, so here's our execution model, exactly the question you just asked. Okay, we have a single thread that resides within a thread block. Okay, threads know their own thread ID, blocks know their own block ID, and then we have a grid of thread blocks. Okay, so it's sort of a hierarchy of parallelism here, right? Threads are parallel within a block, blocks are parallel within a grid. Okay, typical program, maybe you have 128 threads within a block, and you have, tens to hundreds to thousands of thread blocks that you throw at the machine. And the hardware figures out how to distribute those around. You don't have to worry about it as the programmer. Okay? So threads know their own thread ID. They know their own block ID. They have a sync threads command that allows you to do this barrier that we showed a minute ago. And here's the way that you launch a thread. Well, we'll do it this way. Okay. So how do we actually call this thing? What does this look like to us as the programmer? Okay? So we declare things as a kernel. Okay? The kernels are global. Okay? Don't worry about that. We can declare variables as shared and say that means that this will reside in the shared data cache. And all threads within the block can access that. This is how we actually call a kernel. And this says, I want to call this kernel over a grid of 500 blocks, each of which has 128 threads. Okay? So we make this call, and it's going to launch 500 times 128 threads, organized into 500 blocks. This is a 1D kernel and a 1D grid and a 1D block. Okay? If we do memory allocation, that's done explicitly. If we do memory copies, that's done explicitly. So just like you have malloc and free in the CPU memory space, you have malloc and free in the GPU memory space. Okay, so if we want to declare like vector addition, right? So we have this big vector, and you want to add it to another big vector. This is what it looks like. So this says I'm a kernel. Okay, I'm going to take in an input vector of floats, an input vector of floats, and I want to add those pairwise to give me an output vector of floats. So this is what the program looked like. Okay, so you say my index Okay, so we have a bunch of blocks here, and this is block 0, block 1, block 2, block 3. Okay? Then we have, this is block dim x, so how many threads are here in this block? How many threads are here, and so on. Okay? So he wants the 0th element, he wants the first element, he wants the second element, and so on all the way down. And you have to figure out which element is yours, and this is the way you figure it out. You say, which thread am I in the block, plus the offset of the number of blocks. Okay? So every thread will have a different index, and then this just looks like C, right? Read my element here, add them together, and put the result out here. Okay, so there's a vector addition. Keep in mind we write this one program that looks like it runs on one item, and then we run it over all the items. Okay, so this kernel is meant, it can work if you just run it on one item, but the good part of it is it's going to run over millions of items if you ask it to run over millions of items. Okay, you cool with that? Okay, what does this look like on the host? All right, so on the host, you say, okay, the first thing I'm going to do is I'm going to allocate in the CPU memory 2 arrays for I and B. You're going to fill them up. Then we're going to allocate A, B, and C on the device, on the GPU. Okay, so instead of calling malloc, we call CUDA malloc, okay, to say allocate me space on the GPU. Okay? Then we're going to copy A and B from CPU space to GPU space. So that's going to copy them from host to device, from CPU to GPU, over the PCI Express bus. Okay? Then we call the kernel. Okay? Vector add over 256 blocks of 256 elements per block on those pointers into GPU memory space. Okay? Then when we're done, we're going to copy it back, right? We'll copy device to host, and then call CUDA free. Okay? So this will totally run on the GPU, as long as you fill in all the dots, I guess. Okay? But real CUDA code, this is what it actually looks like. So, and this is just scaffolding code. The harder part is this. You know, when you want to make it run something interesting, and making it do it in a parallel-friendly way, that's the tricky part. Okay? Any questions about what we see here or what we see here?
How does this align with the flowchart you showed us? How the CPU prepares the input and.
Okay, great. Okay. Let's draw that. Okay, so CPU, GPU. Okay, so I guess this is allocate CPU memory. Okay, then we fill CPU memory. Then we copy to GPU. Okay, then we call the kernel that runs over here. Then we copy the result back here. Okay, so allocate CPU memory, that's the first two lines there. Okay, that's just calling malloc. Fill CPU memory, well, that's the third line that says initialize HA and HB. Okay, this is host. Okay, sorry. What goes in here is allocate GPU memory. That goes here. Okay, that's the CUDA malloc calls. Okay, this is the copy, CUDA mem copy. Okay, we call the kernel with the bottom line, and what's not shown is bringing it back when we're done. Cool?
Just a quick question. So does CUDA have a stack? Is there a stack on the GPU? Like
stack of what?
Of like when you said in the other slide you had like int index or indx equals that. That would usually go on the stack.
Okay. So each thread processor has registers. Okay. So this would go in a register.
So there's a maximum amount of, like, you can't say int idx 1, 2, 3, 4, 5 equals this. This is a maximum number.
Right. Okay. So this is actually really important for performance. So let me go into that. So you could envision that you could eventually make that number so gigantic as to exhaust the number of registers. CUDA has the capability of spilling that to memory if it needs to. And so it calls that, and is a horrible term, local memory, even though it's out in GPU DRAM. But it can allocate space it can spill registers to memory if it needs to. Okay, let me explain something else that's very important from a performance point of view. Okay. This is our watt of registers per thread processor. Okay? We would like to have as many threads busy on this processor as possible. Because if we have lots of threads resident on this processor, we can do a better job hiding latency. It is less likely that we're just going to be sitting around waiting for everybody to come back from memory. Okay? So we have all these registers. We have 1,000 registers or something. Okay. Now, let's say our program takes 512 registers. Okay, we have 1,024 registers. Okay? And we write a program, and that program requires 512 registers. Okay? What the hardware will do is divide that up so that we have 512 registers here, 512 registers here, and we can have 2 threads resident. That's all. Can't have more than 2 threads unless we're going to spill the memory. That would be very bad. Okay? However, let's say we do a better job and we write a better compiler. Okay? And it turns out we can figure out how to do it with 256 registers. Okay? Then we can have 4 threads resident. Okay? If we do an even better job, we can have 8 threads resident. That's really cool. Okay? So what are the ramifications of this? First, it's really important that you have a lot of registers. Because the issue is, at least with early NVIDIA hardware, to first order, your performance was proportional to the number of threads that you could keep resident at a time. If you went from 2 threads resident to 4 threads resident at a time, your performance would double. Okay? And it's because you were spending most of your time waiting for memory to come back. So if you had 4 threads resident, 4 threads would run, everybody would wait. Otherwise, 2 threads would run, and everybody would wait. So you're twice as fast by having twice as many threads. Okay, so having lots of registers is important. And so the latest NVIDIA hardware, the GTX 200 series, has twice as many threads per register, twice as many registers per thread processor as the processors that came before. Okay, the second thing that's really important is that your compiler should do a great job of minimizing register usage. In fact, it is probably the most important thing that you do. If your thread runs twice as slow and uses twice as few registers, you're probably better off. Because you don't care how long it takes one thread to run. You care about how many threads you're running at the same time. Okay? So NVIDIA spends this enormous amount of resources doing better register allocation. So when you get a new driver and it runs faster, Okay? A lot of the reason is because they're doing a better job with the register allocator than they did before. They can keep more threads resident. They're not sitting around as much waiting around. So register allocation is really important.
But there comes a point where, I mean, no matter how many you would try to add to the, like it gets to a sustainable level where no matter how many you keep in, more you would add, threads you would add to the thread processing block, they'd still, be the most latency hiding ability or whatever.
Yes. So you could probably think that if you have enough threads to cover any latency,
right,
okay, then you're probably in good shape. So the question is, how many threads is that?
And that's kind of hardware dependent, which is kind of hard to, be dealt with on the software side when you're, creating your program. So,
so the answer is that's actually a lot of threads. So just as a thought experiment, let's say it takes 500 cycles to go to DRAM. And that's a pretty optimistic number, actually. Okay? And let's say you run 10 cycles, and then you go to DRAM. Okay? It means that you're going to need 50 threads resident to be able to cover that latency. Because 50 threads are going to wait 10 cycles each. Right? That's a lot of threads to keep busy. You need a lot of resources to keep 50 threads busy. And that number goes up with every generation. Memory is getting faster, slower than compute is getting faster. So if this generation it's 500 cycles to go to DRAM, the next one's going to be 1,000 cycles to go to DRAM, and so on. So yes, there is that number. Rarely do we hit that number. That's sensible? Okay, so this is really important for performance reasons. And so certainly try to minimize your register usage if you're a programmer. Okay, so here's another issue. And this is this issue of divergence. And we talked about this a little bit as well. Okay? We have, and I'm going to use this number, it's going to sound a little weird. We have 16 processors that run in lockstep. And you say, wait a second, John. You said there's only 8 processors per multiprocessor. I say, yes, that's true, but those processors are double clocked. So in practice, it's like there's 16 processors that run. Take my word for this. Okay. So there's 16 of these guys running at once. Okay. The problem is, what happens when this thread takes the branch this way and this thread takes the branch this way? Okay. What it means is that when we're going to the left, this guy's asleep, and then we have to run the whole thing over again and then go where it goes to the right, and this guy's asleep. And if all 16 of these guys take different branches, then it's going to run 16 times as slow as if only one of them, if all of them took the same branch. So one of their goals has been to reduce this branch granularity as much as you can. So they've tried to do that, right? And so when they talk about inefficiency, only when divergence exceeds native machine width. The native machine width is 16 threads wide. So if the divergence is within that, then you're going to run into some performance penalties. But they do a lot of handling of the details of thread bookkeeping and so on inside this. So the hardware takes care of a lot of that. Okay, so if you're actually, let's go one more. If you're actually writing NVIDIA programs, then you write a program in sort of C++ with some CUDA stuff in it. You run it through this magic NVCC compiler, and it splits it out into 2 pieces of code. One piece of code is CPU code that's going to run on the CPU, and that'll just get compiled by Visual C++ or whatever. But the GPU pieces of the code will go to an assembly language called PTX. Okay? So then in their driver, they have PTX, and they turn it into object code. Okay? And this is done runtime in their driver. This is what's going to actually run on the GPU. They actually have a multi-core compiler now where you can take PTX and make it run on multi-core CPUs, which is pretty cool. So you could have a backend for that as well. All right, that's all I got on CUDA. What questions do you guys have on CUDA? Everything else in this whole course is going to be back to like hardware GPU stuff. So now's your big chance. Go ahead.
Is there any emulation for CUDA so that we can use the CUDA without the NVIDIA hardware or something like that?
Yes, and that's really welcome because it's really hard to debug on the hardware. So you can run any CUDA program in emulation mode. It's just going to run it on the CPU. It's slow, but you can run it in printf and do whatever you want to. So when you compile it, you either compile it for runtime GPUs or for CPU emulation. So it has like a -mu switch. Yes, it's very nice. They're working on debuggers for hardware. I don't think those are quite here yet, but debugging parallel programs is hard, and it's a very interesting research problem. How do you debug parallel programs? That's not at all answered yet.
How do cards like the G80 and above fetch memory? Because you imagine that you won't have like a memory for every thread. So you want like all the threads to come in. There'll be one huge batch to memory at once.
Yeah, so we have this 16 here. So what actually goes out to memory is a request that's basically 16 times 32 wide. Okay? Right, so that's big. That's 512 bits wide, which happens to match the memory system, right? So the memory system actually has a 512-bit data bus on the latest chips. So you're going to send out this request, and you're going to ask for 512 bits to come back. Well, if all these guys ask for something that's nice and contiguous, okay, then you're going to get great bandwidth there. You're going to be able to do the maximum bandwidth of the machine. If this guy asks for this weird piece of memory and this guy asks for some other piece of memory and so on, it's going to have to go to memory 16 times to do that, because all it can ask for is a 512-bit wide piece of memory. So it's in your best interest to structure your memory accesses such that they are what NVIDIA calls coalesced, so that they're all in this big chunk. And they're very specific about what the rules are there.
So I tried to install CUDA, and it took a couple hours to realize that the GeForce 78 whatever cards aren't supported.
Not CUDA capable.
And I don't understand why, because CUDA is just on top of OpenGL. They're tricking the hardware.
So I don't want you to feel that way, because CUDA is not on top of OpenGL.
Okay.
Okay. There's sort of our picture, but OpenGL does not come in. You have DirectX, OpenGL, CUDA. They are parallel. It is not on top of OpenGL, and that's sort of the biggest difference between GPU computing and GPU. GPU goes through the graphics interface. GPU computing like CUDA does not.
Okay.
So very important discrepancy. Okay, so in OpenGL, there's no way to like talk to a parallel data cache, right? So it's just not in the hardware.
You can still do emulation.
You could do emulation. You're welcome to borrow a card that's CUDA capable if you want. I can totally lend you one. Yeah.
OpenCL.
Okay.
What do you think about? Because I was looking up at that as an alternative to
Okay.
CUDA.
So Apple's coming out with they have done a standard called OpenCL. It's Open Compute Library. They're interested in having an open version of the kind of things that CUDA does. So what can we do as a nice parallel computing language that's going to well use a CPU? So everybody's on board with this plan, which is really exciting. So Intel and AMD and NVIDIA are all going to build software layers for doing OpenCL. Okay, so right now it isn't very different than CUDA. Like if you look at two programs, they look pretty similar. It's pretty easy to translate from one. At least I hear that from people who have looked at these things before. The question is OpenCL going to work? One of the issues is that everybody who's interested in it wants to pull things in a different way. Like NVIDIA wants it to look exactly like CUDA. AMD wants it to look like CUDA, but dumbed down because they don't have some things like the parallel data cache. They want that sort of thing removed. Intel wants it to look really good on Larrabee so that nobody else can run it. Right? So everybody wants something different. And the question is, can all these people get together and write a standard that everybody's happy with, that everybody supports well? Today, CUDA is the best performing one. I hear that if you run the same code on OpenCL or CUDA is substantially faster because the drivers are more stable and well-known. There's no telling who's going to win. For what it's worth, our group is pretty much doing CUDA computing these days. But we're certainly watching OpenCL, and if it turns out that's going to be big. When I write proposals, they don't like me using CUDA. They'd much rather. So if not only for that reason, we'll look at it very, very closely too. So I might be teaching something very different next year. The deal is you can't buy CUDA, you can't buy an OpenCL machine today. Nothing runs OpenCL.
Oh.
So the next version of the Apple OS, which will come out in the next 6 months, that'll run it, but that'll be the only thing that runs it. It needs to get on other platforms before it's going to be successful.
So, Manu, one of the things you mentioned is that the data you compute can go directly to a texture and be rendered to a frame buffer.
Yes.
Can that be done without having to transfer back to the CPU?
You guys might be able to answer this better than I. So the CUDA term for this is interop. You can interoperate between CUDA and OpenGL or DirectX. So my understanding is the DirectX transfer is really good and instant, just move a pointer, right? OpenGL is supposed to be getting better in the latest beta, the 2.1 beta. It's still a little kludgy though, and interop is known to be something that's slow but is getting much better as time goes on.
And is that a CUDA-specific call or method? How do you do that?
I'd have to refer you to the docs there.
Okay.
Have you guys done this?
Yeah, there is a CUDA call, I think. It's like I forget the exact call name, but you basically send it like an OpenGL data type, and theoretically it's supposed to just know where it is in memory and work with it. But as he was saying before, if it can't find it, which is often the case, it'll copy it back to CPU and then re-upload it. So it's just going to destroy any kind of real-time rendering you're trying to do.
For your research, I would count on it working correctly, only because I don't think it's far from working correctly.
Okay.
Okay. I mean, they're very aware of the factor's performance. It's just that they know it's important. Have a good weekend.